Good day, students! This video is a lecture on quadratic functions, covering everything from definition to solutions. To guide you through this lecture, the outline will be flashed for a while for your reference. You may pause if you feel like taking notes.
You will see the definition of a quadratic function, examples of quadratic functions, methods of solving quadratic functions, the vertex form of a quadratic function, the quadratic formula, and graphing a quadratic function.
To start our lesson, let us first define what a quadratic function is. A quadratic function is defined algebraically as either y is equal to ax squared plus bx plus c in standard form, where a, b, and c are real numbers, or y is equal to a times to the quantity of x minus h quantity squared plus k in vertex form, where a, h, and k are real numbers. For both cases, a cannot be equal to 0. The domain of x values are always the entire set of real numbers, while the range of y values are dependent on the y value at the vertex and open of the graph. Values at the vertex may be called the graph's maximum or minimum depending on the open of the graph. To generate a quadratic function, one must only follow the definition given at the slide before. Examples are y is equal to 8x squared plus 2x plus 5, and y is equal to 2x squared plus 1, and the last, y is equal to 4x squared minus 3x. And the simplest of all, y is equal to x squared. As you can see, there are different forms as long as a is not equal to 0. There are several ways of solving a quadratic function. You will get the same answers regardless of the method. And the best method depends on you, the solver. The first method to be taught to you will be factoring. Following factoring would be by completing the square. After that would be the standard quadratic formula. The last visual way of looking at the solutions would be graphing. Let us first apply the method of factoring. Given the function y is equal to x squared plus 10x plus 25. Find the zeros of the function. Note that zeros of the function mean the x values that make y equal to 0. The solution is as follows. Here is another example of a function that can be easily solved by factoring. Y is equal to x squared plus 5x plus 6. This time, find the x-intercepts and the y-intercept. Note that the constant c in the definition is equal to the y-intercept, which in here is equal to 6. To solve for the x-intercepts, simply factor out the standard form. The solution is as follows. We will now move on to completing the square. It is called so because this is a process that would allow the solver to manipulate a hard-to-factor equation into an easy one. The important formula here is b over 2 square, where b is the coefficient of the x term in any function of form y is equal to ax squared plus bx plus c. Let us now start solving and converting a function by completing the square. Given y is equal to x squared plus 10x minus 5 Using the magic formula b over 2 square, we get y plus 10 over 2 square is equal to x squared plus 10x plus 10 over 2 square minus 5. Note that we need to keep the equation equal. Further simplifying leads us to y plus 25 is equal to x squared plus 10x plus 25 minus 5. Now we can factor, which will lead us to y plus 25 is equal to the quantity x plus 5 quantity squared minus 5. Further simplifying, we get y is equal to the quantity of x plus 5 quantity squared minus 30. Wait a minute, remember the other definition of the quadratic function? The vertex form of any real quadratic function is of the form y is equal to quantity x minus h quantity squared plus k. Recalling our answer on the last problem, we got y is equal to quantity x plus 5 quantity squared minus 30. This was from a given of y is equal to x squared plus 10x minus 5. By the transitive property, we can say that y is equal to x squared plus 10x minus 5 and y is equal to the quantity x minus negative 5 quantity squared minus 30 are one and the same function. Therefore, completing the square is useful for converting the function into vertex form.
Take our same converted equation from last slide, which is y equals x minus negative 5 quantity squared minus 30. Now, by virtue of the form y equals x minus h quantity squared plus k, we can say that 5 is equal to h and negative 30 is equal to k. The vertex form has a special property wherein the coordinate h, k is the vertex of a certain quadratic function. Therefore, if asked for the vertex of y equals x plus 5's quantity squared minus 30, we can simply say the vertex is at coordinates negative 5 and negative 30. This trick will only work if and only if the function is represented as vertex form y equals ax minus h squared plus k. Let us set aside completing the square for a short bit as I teach you the standard quadratic formula, where 0 equals ax squared plus bx plus c. X is derived as the result of the equations shown, where a, b, and c correspond to the a, b, c coefficients of the standard form. Simply substitute in values for finding the x-intercepts. You will see an example of solving by the formula on the next slide. Given y is equal to x squared plus 5x plus 6, solve for the x-intercepts of the function, if any. We all know that by factoring we can get this, but for the sake of comparison, let us see if the formula is also effective. Now that you are equipped with the different methods of solving for a quadratic function, let us now proceed to visualizing it. All quadratic functions follow a U-shaped curve. This U is called a parabola, depending on the parity or the sign of coefficient A on both standard and vertex forms of the quadratic function. As a property of the graph, it opens upwards when a is positive and opens downwards when a is negative. Further discussion on graphs would be well supplemented with an actual graph in the slide. Given our classic example y equals x squared plus 5x plus 6, we can already tell that the x-intercepts are at -3 and -0. Further inspection of the equation and we can already plot the y-intercept 6. Remember that in standard form, y-intercept is always equal to c. Since a is positive, it also opens upward. We now have enough information to form a parabola. With this, we form the U-shaped graph and place arrowheads to indicate infinite continuity. Given a function y equals x minus -5 squared minus 30, how are we to interpret its graph? Well, we know that it is in vertex form, thus we can say that the graph has its minimum value at -5, -30, since it does open upward because a is positive. To recap, a quadratic function has two forms, standard and vertex form. A quadratic function can be solved through either plain factoring, completing the square, or by the quadratic formula. It can also be better visualized by graphing.